And now I will read the files into Fluent. So from the file menu, click on read and mesh file. And this is common for all the cases we do in the Fluent. And from input files, we have the 4 meshes, and you can go for any of one of them. And here I will go for the pipe tetraprism mesh. And first of all, we will look for the mesh display. So you can display the mesh from here. And if you increase the size of the display window by decreasing size of the other windows, you can feel here that you can zoom here. And right now we have the inlet from this side, which has the blue color. And by default we have some colors. The outlet is colored by the red color and the wall is colored by the white or gray color. So you have to check that if the color is not appropriate, then you have to check that we have something wrong here. So as you can see here, that the inlet defined as the wall. So you can change from here and make it velocity inlet or pressure inlet. And after that, if you check the mesh display, you can see the color of this face is now blue. And you can hide the faces, so click on display and this will hide the faces. And now you can just see the wireframe or just the cells on the different boundaries. And starting from the journal, you can see here that we have the pressure based solver. So we keep this one for the any flow which is incompressible, and we saw this case by the pressure based solvers. And for the flows which has the Mach number greater than the 0.6 or maybe more than 0.3, then we go for the compressible flow dynamics. And in that case, we have to use the density based solver, which is well suited for these type of flows when the flow is compressible. And from the info, you can check the size of the mesh. So it will tell you the levels, cells which are here. 1,45,000, number of faces are 3,47,000, and number of nodes are the 60,000. And there are 4 partitions because we are using parallel version of the Fluent. And since I have the maximum 4 cores in my computer, that's why I'm using 4 cores, and that's why it is dividing mesh into the 4 partitions. And then you can check the units for different things. For example, for area it's a meter square, and by default we will get the length in the meters, and the angle if necessary to change, so it will be in the degrees. And you can also change to the radians, angular velocity radians per second. You can change this one to the RPM, but right now we don't change anything here, so just close the window. And you can check the mesh from here. And the important thing which you should look for is that you should not have the negative volume for the minimum volume. It should be some positive quantity. This may be very low number depending on the cell size in your mesh, but in any case this should not be the negative value. And you can check the quality of the mesh. So minimum orthogonal quality should not be less than the 0.01, and right now we have the 0.17. So 0 is the worst and the 1 is the best. And the aspect ratio, which is the ratio of the cell length to the cell height or cell width, is 26, which is good enough. It should be less than the 100. And in the boundary layer, it should be less than 1000 for single position solver, and should be less than 10,000 for double position solver in the boundary layer. And also you can scale the mesh if necessary. For example, if the mesh was created in the inches, in that case you have to select the mesh was created in the inches and then click on the scale to scale the mesh to those units. But since this geometry was created in the meters, so we don't do anything here. And you can also check that the length of the domain is 8 meters in the z direction, which is the length of the pipe. And from problem description, you can see that we have the length of the pipe is around 8 meters and diameter is 0.2 meters. And these are boundary conditions. For Reynolds number 100, we can calculate if you put the value of density equal to the 1, velocity 1, diameter is 0.2, and we assume that the Reynolds number is 100, which is to keep the value less than 2000, so that flow will remain the laminar flow. And also if you increase the Reynolds number, then you have to increase the length of the pipe as well, because we want to have the fluid flow. And after putting these values, you can calculate the viscosity from this formula, and these four numbers are known. So viscosity comes out to be the 2 × 10⁻³ kilogram per meter per second. So you can see here that we have the length as the 8, and in the y we have the dimension as a -0.1, and in the y maximum is a +0.1, so it's a 0.2. Same is case for the x direction. This is all about the case import and the case checking. And the time will be the steady state, because we are going to solve this case as a steady state, and there is no gravity in the flow. So this is all about the how to import the mesh and then check the mesh with the different matrices in the Fluent.